In this video, I want to talk a little bit more about two-force members. Recognizing a two-force member can really help us when we're drawing our free body diagrams because it reduces the amount of unknowns we have in our equation. If I look at this member ABC here, and I recognize that there's pin connections at A and B, I could draw my free body diagram with the 400 Newton force that's applied at C, and then I'll draw a pin connection at B, which has an X and a Y component. I'll draw it this way. When I draw these vectors, it's a little bit arbitrary which way you draw it. You just need to make sure you match your signs when you write out your equilibrium equations. And then I have a pin at A. Now, if I wanted to solve this problem, I have all the geometry for this shape, and I have three equilibrium equations. My sum of the forces in the X, sum of the forces in the Y, and my sum of the moments all have to be equal to 0. But I have four unknowns. I have by, bx, ay, and ax. So I'm going to be kind of stuck here unless I can simplify this problem. Well, I can look at this little linkage here, BD, and I'll draw a free body diagram of that to show you that that's a two-force member, and that simplifies our problem. So let's look at this linkage here, BD. I'm going to draw my forces here for BD. At point B, I have a pin, and I'm going to draw them equal and opposite to what I drew in the other diagram. So this is going to be BY, and this is going to be BX. And so recognizing that this force over here is the force of the linkage BD pushing on member ABC, and this force here is the force of member ABC pushing back on the linkage. They're equal and opposite forces. And then I'll draw my forces at D here. So I have dy and dx. And it's going to be helpful to me if I define the line of action of this two-force member. Even though it's curved, these forces both act between these two pins along this axis here. And so let's think about a couple things here for this two-force member. So if I draw, we know that if we write the sum of the forces in the x direction, that dx has to be equal to bx, and dy has to be equal to by, for this particular example. So that the y components and the x components have to be equal to each other, and so I could draw these vectors. I'm going to erase these and just draw a pair of vectors. So I'll combine those vectors. So I could draw this. So this was maybe bx and by. And dx and dy. So I've drawn these two to satisfy that criteria where bx and dx are equal and by and dy are equal. But if you look at this, now I've drawn a couple. I've drawn two forces that are separate, they're equal and opposite and are separated by some distance. And so this piece is not going to be in equilibrium. It's going to want to rotate the way I've drawn it here, like this. And so the only way I can draw these two forces is if that they point, so they don't form a couple, is if they point towards each other, which is another way to say that they have to point along the line of action between those two members. And so when I'm drawing my free body diagram here, I could recognize that the direction of the magnitude of that force, when I write it in the x and y components, it has two unknowns. I could simplify that. I could say that this is the force in member BD, and it's acting at this angle, which is 45 degrees. Now, when I try to solve this problem, I only have three unknowns. associated with it. So a lot of times we'll see members when we have a weightless link that's connected by pins on both sides. That should be an obvious clue to you that it's a two-force member. But it doesn't have to be connected by pins on both sides. So I wanted to look at this problem here. And this is going to be a problem where we're going to have to use friction. And so that's something we talk about later in the course to stay in equilibrium. If we just assumed that we had normal forces here, these members would want to, if I drew this member AC, let's draw that member out. So I have AY, and I have maybe some force at C acting from CB, and then I also have some weight acting down on that member. If I look at this problem without friction, if I take the moment at this point, it's going to want to rotate this way. That's intuitive. If this was a super smooth surface, this device would want to slip down and do the splits if we didn't have friction. But if we have friction, notice there's no pin here, but if we have friction, then now we know that this member, that the friction in the x direction has to be equal to the force pushing back at C, and AY has to be equal to the weight pulling down. And if I think about the components of those, if I add them together, so if I add AY and friction together, they have to act along this line of action. Any other force, if I had it acting at any other angle, we'd have a couple, and that would cause this thing to want to rotate. So this member, even though it's not connected by pins on both sides, is going to be a two-force member. And same with the member here at CB. One more example. This is going to be called a frame, and it's supporting a couple different loads here. And we'll learn how to analyze this later on in this class. But right now, I just want to try to identify what members are two-force members. So we have 4 members that make up this frame. We have member AB, which is connected by pins on both sides. We have member BC, which is connected by pins on both sides. We have AD, and we have this member here, EDC. Let's start by looking at the top member here. It's connected by pins on both sides, so we have a pin connection on either side, but that's not the only criteria for it being a two-force member. It also has this distributed load pointed down, which we could simplify with a resultant force acting right in the middle of the beam. And then we have these pin connections on either side. So this has forces applied at more than 2 points along the beam. It has forces applied at A, in the middle, and at B, so it is not a two-force member. What about AD? Well, this has pin connections on both sides, and if the mass of that member is negligible, then yes, that's going to be a two-force member. It only has forces applied at point A and point D. So we'll highlight that one as a two-force member. Moving over to BC, it has forces applied at the pin at B and forces applied at the pin at C. It also has this 5 kilonewton force applied down here at C, but that's applied at point C. So we still only have forces applied at points B and point C and nowhere else on the beam. And so that's going to be a two-force member. Last, we have this member here, EDC. It has pins on both sides, but it also has the force of this member coming down the middle here. So as forces applied at 3 points, it's not going to be a two-force member. So the two-force members in this problem are going to be AD and BC.